Welcome to the AWS Certified Cloud Practitioner Prepcast, where we guide you through everything you need to know for your certification exam. Whether you're just starting or looking to refine your knowledge, this course will set you up for success. Brought to you by baremetalcyber.com. Let's get started. Amazon EC2 instances require storage, but AWS provides two fundamentally different approaches: Elastic Block Store, EBS, and Instance Store. Understanding the differences between these two storage models is crucial for making the right architectural choices. EBS offers persistent, network-attached block storage designed for durability and flexibility, while Instance Store provides ephemeral, host-level storage with unmatched performance but no persistence. In practice, this trade-off boils down to persistence versus speed. Choosing the correct option depends on workload requirements, balancing durability, performance, and cost against operational complexity. EBS volumes come in multiple types, each designed for specific performance and cost profiles. GP3 volumes are general-purpose SSDs that balance price and performance, making them the most common option for everyday workloads. IO1 and IO2 are provisioned IOPS SSD volumes, offering predictable, high-performance storage ideal for latency-sensitive databases. Saint1 volumes are throughput-optimized HDDs designed for large, sequential workloads such as big data or log processing, while SC1 volumes are cold HDDs for infrequently accessed archival-style data. Understanding these types ensures you choose the right balance between performance characteristics and storage costs. Performance in EBS is measured by two key metrics: IOPS, input/output operations per second, and throughput. IOPS represents the number of small read and write operations a volume can handle, while throughput measures the volume of data transferred per second. Workloads like transactional databases are sensitive to IOPS as they involve many small operations. By contrast, analytics or log processing systems care more about throughput as they transfer large sequential datasets. Recognizing which performance signal matters for your workload ensures that you select the appropriate volume type and provision resources effectively. All EBS volumes support encryption at rest using AWS Key Management Service, KMS. This means that data stored on the volume, data moving between the volume and the instance, and snapshots created from the volume are all encrypted seamlessly. Administrators can use AWS-managed keys for simplicity or customer-managed keys for greater control and auditability. Because encryption is configured per volume, organizations can apply security policies granularly, ensuring that sensitive data is always protected without introducing significant performance overhead. Encryption is a default best practice in modern architectures. EBS volumes are availability zone scoped, meaning that a volume exists within a single AZ and can only be attached to instances running in the same zone. This design ensures low-latency connections between volumes and instances but requires awareness in multi-AZ architectures. For resilience, administrators often replicate data across AZs using snapshots or design high availability by deploying instances with attached volumes in multiple zones. Understanding this AZ scope is key to designing systems that remain resilient while balancing performance and costs. One of the most powerful features of EBS is snapshots. These are incremental backups of volumes stored in Amazon S3. Snapshots capture the state of a volume at a given point in time, enabling disaster recovery, data migration, or replication workflows. Because they are incremental, only changed blocks are stored after the initial snapshot, making them space-efficient. Snapshots can be copied across regions or shared with other accounts, extending their utility. They serve as the cornerstone of backup and recovery strategies for workloads that rely on EBS. To speed recovery from snapshots, AWS provides Fast Snapshot Restore, FSR. Normally, Restoring a volume from a snapshot can lead to initialization delays, as blocks are lazily loaded when accessed for the first time. With FSR, specific availability zones can be pre-warmed so that restored volumes are immediately performant. This is especially useful for workloads where downtime is costly, such as production databases. By paying for FSR on selected snapshots, organizations can combine durability with rapid recovery, ensuring both resilience and performance. EBS also supports multi-attach for I/O1 and I/O2 volumes. This allows a single volume to be attached to multiple instances within the same AZ. Multi-attach is primarily intended for clustered applications that can coordinate simultaneous access to shared block storage. However, its use cases are narrow, as most applications are not designed to handle concurrent block-level writes. Without proper coordination, data corruption can occur. Multi-attach illustrates AWS's attempt to extend EBS's flexibility, but should be used only for very specific scenarios like clustered file systems. For most EC2 instances, the boot volume, the root device that stores the operating system, resides on EBS. This design ensures that an instance can be stopped and restarted without losing its root file system. Administrators can also create Amazon Machine Images (AMIs) from EBS snapshots, simplifying the replication of server configurations. Booting from EBS volumes separates system state from compute, making it easier to scale and recover. By contrast, when using Instance Store as a root device, the operating system disappears when the instance stops, reinforcing EBS's value for persistence. In contrast, Instance Store provides block-level storage that is physically attached to the EC2 host. Often implemented as high-speed NVMe SSDs, Instance Store delivers extremely low latency and high I/O performance. Because it is directly connected to the underlying hardware, it bypasses the network abstraction of EBS. This makes it ideal for workloads like caches, temporary buffers, or high-performance analytics, where raw speed is more valuable than persistence. Instance Store volumes often outperform EBS in raw I/O, but they come with significant limitations. The defining characteristic of Instance Store is its ephemeral nature. Data is lost when the instance stops, hibernates, or terminates. Even hardware failures at the host level can wipe data. This makes Instance Store unsuitable for workloads requiring persistence. Instead, it should be used for data that can be regenerated, replicated, or discarded without consequence. Examples include web caches, scratch disks for video rendering, or temporary storage in scientific simulations. Ephemerality is both its weakness and its design intention disposable speed at scale. Because Instance Store resides on the host hardware, it supports extremely high I/O and very low latency use cases. Applications like NoSQL databases, in-memory analytics, or real-time media processing can benefit from these performance characteristics if they implement replication or persistence at the application layer. For example, a distributed caching system like Redis can run on Instance Store volumes, using replication to prevent data loss. The key is that durability is pushed up to the application, freeing the storage layer to focus entirely on speed. Unlike EBS, Instance Store does not support snapshots or incremental backups. If persistence is required, applications must implement their own data management, such as writing logs to S3 or replicating across multiple nodes. This increases developer responsibility but allows flexibility in designing high-performance systems. The lack of native backup support reinforces that Instance Store is meant for temporary fast-access workloads, not long-term data storage. Organizations must carefully decide whether the trade-off between performance and durability fits their needs. Finally, cost considerations differ between the two storage models. EBS volumes are billed per gigabyte provisioned, with additional charges for IOPS or throughput depending on the volume type. Instance Store, by contrast, is included in the price of the instance type and cannot be expanded or detached. This means that while Instance Store may seem cheaper, it lacks the flexibility of scaling independently from compute. Exam questions often frame this as persistence versus speed, EBS for durability and control, Instance Store for raw performance. Knowing these trade-offs ensures the right choice for each workload. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. When choosing between EBS volume types, one of the most common questions is whether to use GP3 or IO1/IO2 for database workloads. General-purpose GP3 volumes provide baseline performance with the ability to provision additional IOPS and throughput as needed, making them suitable for many transactional systems at a lower cost. However, latency-sensitive enterprise databases like Oracle or SQL Server often demand the consistent, high-performance guarantees of IO1 or IO2 volumes. These provisioned IOPS volumes ensure predictable performance even under heavy load. The trade-off is cost. GP3 maximizes value, while IO1/IO2 maximize stability for critical applications. For throughput-heavy workloads, AWS offers Street 1 and SC1 volumes. These HDD-based options are designed not for transactional workloads but for large, sequential data operations. The Saint 1, or throughput-optimized HDD, excels at big data analytics, log processing, and data warehouses where workloads read or write in long, continuous streams. The SC1, or cold HDD, is the lowest cost option and is designed for infrequently accessed datasets where performance is not critical. These classes illustrate that not all EBS volumes are SSD-based. Matching the right disk technology to workload patterns is key to cost-effective architecture. Organizations can also deploy RAID strategies on top of EBS volumes to balance performance and resilience. RAID 0 can stripe data across multiple EBS volumes, increasing IOPS and throughput for workloads like high-performance databases. RAID 1 can mirror data, providing redundancy beyond what individual volumes offer. While AWS already ensures durability through replication within the infrastructure, RAID can be valuable for specific performance or redundancy goals. However, it introduces additional complexity and cost, and for many workloads, EBS features like snapshots and multi-AZ patterns provide sufficient protection. A disciplined backup runbook is essential for any environment using EBS. Snapshots form the backbone of these strategies, with schedules defining how frequently backups are taken and retention rules determining how long they are stored. For example, production databases may require hourly snapshots retained for a week, while less critical workloads might use daily snapshots with a shorter retention window. Automating these processes with AWS backup or scripts ensures consistency and reduces human error. A clear runbook also ensures compliance with organizational or regulatory requirements for data protection. Complementing backup planning is a restore playbook. This defines how to recover from snapshots when needed, whether restoring a volume directly or creating an Amazon Machine Image (AMI) from a snapshot to rebuild an entire server. Testing restore procedures is just as important as testing backups, ensuring that recovery is not only possible but also timely. Without clear recovery steps, backups remain theoretical. A documented restore process provides confidence that downtime can be minimized during failures, making EBS a dependable part of resilience planning. Encryption practices for EBS require thoughtful policies. By default, volumes can be encrypted with AWS-managed keys, but organizations often prefer customer-managed KMS keys for better control and auditability. Key scoping decisions become important in multi-account setups, where shared keys may simplify operations but increase security risks. Misconfigured key policies can block restores or replication, turning encryption into an operational bottleneck. A clear policy framework ensures encryption supports security goals without complicating daily operations. balancing compliance needs with usability. Monitoring EBS volumes is critical for both performance and cost. CloudWatch metrics provide visibility into read and write operations, latency, and queue depth, while burst balance metrics highlight when GP3 or smaller volumes exhaust their temporary performance credits. Monitoring enables administrators to detect bottlenecks, such as under-provisioned IOPS, before they impact applications. Coupling these metrics with alarms ensures that operations teams are alerted to anomalies, maintaining both system health and financial efficiency. Visibility transforms EBS from a static resource into a managed, dynamic component of infrastructure. Instance Store finds its niche in workloads that rely on speed rather than persistence. Caching layers, scratch disks for video rendering, or temporary buffers in high-performance computing all benefit from the raw I/O capacity of NVMe-backed Instance Store volumes. Because they are ephemeral, these volumes require no snapshot management. Instead, resilience must be built at the application layer, often through replication, checkpointing, or redundancy across nodes. By deliberately offloading persistence to the application, Instance Store becomes a powerful tool for disposable, ultra-fast storage needs. Checkpointing is a particularly important practice when using ephemeral storage. Applications must periodically save state to a persistent medium such as S3 or EBS to recover gracefully if data on Instance Store is lost. For example, scientific simulations might checkpoint progress every few minutes, ensuring that if a node fails, only minimal work is lost. This approach leverages the speed of Instance Store for computation while still anchoring resilience in durable storage. Proper checkpointing design makes ephemeral storage viable for critical workloads, despite its transient nature. AMI selection also plays a role in how storage behaves. Some Amazon machine images are built with Instance Store root devices, meaning the operating system itself disappears when the instance stops or terminates. Others rely on EBS-backed root devices, which persist across instance lifecycle events. Administrators must be mindful of this distinction when choosing AMIs, as stopping an instance with an Instance Store root device results in data loss. For long-lived workloads, EBS-backed root devices are recommended. For disposable compute, Instance Store-backed AMIs may suffice. Multi-AZ designs highlight another strength of EBS compared to Instance Store. EBS is inherently scoped to a single availability zone, but its snapshots allow replication across zones and regions. Combined with auto-scaling groups, instances can be provisioned in multiple AZs with their own attached EBS volumes, providing fault tolerance. Instance Store, by contrast, cannot replicate across AZs without external mechanisms. This means that for highly available designs, EBS is the default choice, while Instance Store requires application-level redundancy and orchestration. Cost hygiene is critical when provisioning block storage. With GP3, administrators can independently provision IOPS and throughput, avoiding over-allocation. Many organizations waste money by over-provisioning IO1 volumes when GP3 could provide sufficient performance at a lower cost. Right-sizing requires regular review of performance metrics to align provisioning with actual needs. This discipline ensures that block storage contributes to efficiency rather than bloating budgets. Instance Store, while included in instance pricing, should also be scrutinized. Choosing an oversized instance just for extra ephemeral storage often wastes compute dollars. Pitfalls abound when working with ephemeral storage, especially when stopping or terminating instances with Instance Store root volumes. Data loss is inevitable in these scenarios, yet inexperienced teams often overlook this fact until it's too late. Similarly, assuming that Instance Store supports snapshots or persistence leads to false confidence. Clear training and documentation help prevent these mistakes, ensuring that teams deploy ephemeral storage only where appropriate. By treating Instance Store as disposable by design, organizations avoid costly misunderstandings. Finally, documenting approved volume types per workload ensures consistency and governance. For example, policies might dictate GP3 for application servers, IO2 for production databases, and Saint1 for data lakes. By codifying these decisions, organizations reduce the risk of misaligned storage that drives up costs or compromises performance. Documentation transforms storage selection from an ad hoc decision into a strategic framework. This consistency supports compliance, cost control, and operational efficiency at scale. On exams and in practice, the distinction between EBS and Instance Store often appears in scenarios that highlight persistence versus speed. If durability and snapshots are mentioned, EBS is the clear answer. If temporary high-speed storage for caches or scratch space is the focus, Instance Store is the right choice. Recognizing these cues ensures accurate answers and effective architectural decisions. The rule of thumb is simple: use EBS for durable state and Instance Store for ultra-fast, disposable data. Each tool excels when used as designed. That concludes today's episode of the AWS Certified Cloud Practitioner Prepcast. Be sure to tune in for the next episode and visit us online at baremetalcyber.com or cyberauthor.me for more resources, including news, mailing lists, YouTube videos, podcasts, and much more.